When an extinction event is serious enough, it leaves an indelible mark in the fossil record. Now, because the fossil record is fragmentary, it can be very tricky, and so we'll look at that in 3.6d also. However, when an extinction event is large enough, it leaves an obvious mark. Now, if we look historically at extinction rates based on fossil evidence, notice it's a little bit imprecise, that there's all these jaggedness, but there's some very obvious upticks, massive in some cases, in extinction rates as we look at the fossil record. And so we have evidence for 5 historical extinction events, and there were probably others even earlier on. For instance, the Great Oxygenation Event, when free oxygen began to build up in the atmosphere, was probably also a mass extinction event. But because we only had single-celled organisms back then, we don't have a clear fossil record of what we had before and what we had after. But it was a massive enough change that it probably had a global impact. But we do have record for 5 extinction events. Now, the causes of these are the exact same as we've already been talking about. In general, it's failure for species to adapt to a changing environment. But when we see species all over the Earth going extinct at incredibly high rates, that's a different thing. And so, in order to be a mass extinction or a cataclysmic global extinction, there needs to be some fairly rapid change. We're talking over geological timescale, so maybe over thousands or tens of thousand years. That's rapid in geological time. And it needs to be something that affects the entire global environment. And there's still a lot of debate as to what caused some of these extinction events, but we are going to look at 2 of them and talk about their proximate causes or their more specific causes, right? Okay, so each of these had a huge ecological impact. The species that survived nearly, in some cases proportionally, we nearly bottomed out. Now, it's going to be very, very difficult. We'd have to get way, way more change than we've ever had to completely extinguish life on Earth. Life is everywhere, and much of it is very different and can adapt to just about any change. At least something will survive, okay? So we've never really come close to having everything go extinct, but some cases we've lost 90 or 95% of species. And what that means is it's like that analogy we talked about in 3.6a. It's like the empty plate. When extinction eliminates species, that means there's new ecological space that organisms can take advantage of, fill up, adapt to, and eventually we'll have new species. But that can be a slow process that takes millions of years to recover from that extinction event. So it's going to have massive ecological impacts. The one that we're going to talk about first is the Cretaceous-Tertiary extinction. And this is an important one, number one, because we've got good evidence about its cause. And number two, this is the extinction event that has most recently impacted our own ecological systems on the Earth. And so the reason that we have large mammals, including you and I, right, but zebras and elephants and even some of the more recently extinct ones, the reason those were able to adapt was because they were filling niches that had been vacated by many dinosaur species. Okay, so the KT extinction, or Cretaceous-Tertiary extinction, happened approximately 65 million years ago. And as people began to dig up dinosaur bones and look at the dates and begin to understand the dates, they realized that very rapidly, within a short period of time, all of the larger dinosaurs and most other dinosaurs went extinct. Now, we know today that a few survived, and those are our modern birds, but that was just one small group of dinosaurs. The vast majority of them were gone. And as people began to examine this layer that marked the boundary between large dinosaur fossils on the bottom and none of them on the top, and not only dinosaurs, but also other large diapsids. So pterosaurs go extinct. Many of the lepidosaurs that are in the oceans go extinct. Ichthyosaurs, plesiosaurs, all these guys are gone after this barrier. And what people noticed is that there was a very high level of iridium in this KT layer. Now, iridium is sometimes called a rare earth metal. We use it in cell phones and other electronics, but there's not a lot of it in most rocks. And so it was unusual to see this elevated level of iridium, and it was found all over the globe. So rocks of this age, from wherever they were, had these elevated levels of iridium. And so this got people thinking, well, what would cause a global increase in the rate of iridium? And what they realized is that some meteorites have high levels of these rare earth metals, and some of them have high levels of iridium. And so there was this hypothesis that a massive meteorite hit the Earth 65 million years ago. It was significant enough and changed the ecosystem enough that it caused mass extinctions on a global scale. And so people began to look for this crater. Now, some craters are pretty obvious. This is a meteor crater from northern Arizona. That's a very obvious impact zone. Okay. Others are, because of their age or because of plate tectonics or even just simple erosion, are a little bit harder to find. And the impact crater for the KT meteorite was very tricky to find. But a couple decades ago, people found this impact crater off the Yucatan Peninsula. The crater itself is actually halfway in the Gulf of Mexico and halfway buried in the jungles of the Yucatan Peninsula. And you can see it very, very clearly using radiometric data and mapping of cenotes, funny enough. So cenotes are like freshwater wells that have formed along the margin of the crater. So if you map the location of all the cenotes in the Yucatan Peninsula, they actually make this semicircular ring that is the margin of the crater. Okay, so we now know that this massive meteorite hit what was then the shallow ocean, and it's now partly on land in Yucatan, and in the nearby, the couple hundred miles around there was just devastated. There were massive energy released from that dust, kicked up into the air. A huge tidal wave, maybe hundreds and hundreds of feet tall, would have washed over much of the area. And notice that South Texas was actually underwater, and much of the southern U.S. was under a shallow sea at that point. But these coastlines would have just been devastated by that. Not only that, but it kicked up enough dust and air, all that iridium vaporized, goes up into the air and then settles down in those sedimentary rocks. But all the other dust caused massive global changes. So not only was it a regional devastating impact there, but it also had a huge impact at the global stage and basically kicked the globe into a kind of a winter or very, very cold ice age period. Most of the dinosaurs went extinct, with only the birds surviving, the plesiosaurs, the ichthyosaurs, the pterosaurs, and many other groups also all go extinct. Now that leaves an opportunity. All those grapes gone from the plate, right? All those species gone from the ecosystem. And now other organisms can fill up that. And the niches that were filled by dinosaurs, large herbivores, large predators, to a large extent were filled by mammals. And so mammals, the age of mammals, sometimes we call the Cenozoic era the age of mammals, because they are the big, dominant, charismatic vertebrates in those ecosystems. The only other mass extinction that we're going to talk about is the Permian mass extinction. This one happened 250 million years ago and marks the boundary between the Paleozoic era and the Mesozoic era. And this is important for a couple of reasons. Number one, it, as far as we know, was the largest mass extinction in the history of the Earth. If we look at sedimentary rocks from the oceans, before and after, about 95% of the species that were present prior to this extinction event are gone, just a few million years later. So it was a massive, massive event. Although there's still some debate about its cause, the most likely culprit seems to be these massive lava flows that occurred over thousands of years in what is now Siberia. So these Siberian traps are ash and volcanic rock spread over hundreds and hundreds of thousands of square miles. So it was just this massive lava flow year after year after year flowing into the ocean, and eventually the chemistry of the ocean, the global cycling of carbon dioxide and nitrogen and all that stuff was impacted so much that organisms just couldn't handle it, they couldn't survive. And so this would be artist's depiction of before in the Permian and then in the early Triassic, which is the first period of the Mesozoic era. And so we have just this very depauperate, not very many species present. Now, eventually, we get back to having as many species. However, the species that fill up the empty space look very different. Some remnants hang on, but the ones that do then evolve and change. And so here we had crinoids and sponges and nautilus that are around a little bit, or at least some of them were, but are much less important later on. We might be replaced with mollusks and vertebrate fish and other organisms. Okay, so know the Permian extinction, that it was the most severe recorded in the fossil record, and it happened about 250 million years ago. Now, it's likely that there are other extinction events that we don't know about prior to 600 million years ago, but there are 3 others that are found in the fossil record. You can look them up. I'm not going to ask you questions about them. They're important for that era, but don't have as much of an impact on our world today. So we won't look at them for this class. Now, as people begin to examine these fossil records, they start to look for patterns, and they start to ask questions about species that they see and which ones go extinct. Why does species A go extinct when species B survives? And so they begin to examine that and examine that. And so one of the questions was, does past success predict survival? And the short answer is no, it doesn't. Oftentimes it can just be chance or luck that a species survives. It might, and we can even think of luck like, so for instance, the only dinosaurs that survived the KT extinction event were the birds. Now you might think, well, that's because they were small and were able to move around and they had feathers to insulate them against the cold weather, and that's all true. But they were lucky in that they had all of these features already in place when the environment changed. It could have just as easily changed to favor, hotter temperatures or other things, and the birds maybe wouldn't have done as well under those. So really, just because you've done well even for millions of years doesn't necessarily mean that you're going to survive the next extinction event. However, there are 3 things that, and 2 of them are listed here, we'll list a third, but there are 3 things that can predict whether or not a species will survive a mass extinction event. The first is geographic range. So the answer to this top question here, does geographic range predict survival? The answer is a resounding yes. So the more widespread you are, the more chance you have of surviving a global extinction event. That's kind of obvious, right? You're living not only in North America, say, but if you're spread into Europe and Asia, then if something big happens in one area of the world, you're more likely to survive. Okay. The other 2 factors that might predict success, I guess I just have one listed here, but there are 2 others. The other one is your degree of specialization. So specialist species that rely on one food source or one little special area where the weather is just right for them to survive are going to be more susceptible to extinction. If you're a generalist, then you will have a better chance of surviving, because if one of your food sources is impacted or goes away, you can rely on the other ones. Or if a new predator is introduced, but you're able to respond to that new predator, then you'll be able to survive. Okay, so generalists tend to do better when there are mass extinction events than specialists. And then the final one is biodiversity. So dinosaurs survived because they were a very biodiverse group, and a few of them were able to fit in the niches that were around after that meteorite hit. Other groups, like the pterosaurs, were not very biodiverse, right? So the pterosaurs had just basically one major way flying around. They had some size variation and food variation, but they weren't as diverse as the dinosaurs. And therefore, they were unable to survive that extinction event. Okay, so number 1, geographic range increases survivability of extinction events. Number 2, being a generalist instead of a specialist increases survivability. And number 3, the biodiversity of the group you're looking at, that also increases the chances that that group will survive an extinction event. So go over and review and make sure you know those 3 things.